Okay, this is section 17.2, current and drift speed. And let's go here to our PowerPoint. Current depends on the average speed of the current of the charge carriers in the direction of the current, the number of charge carriers per unit volume, and the charge carried by each charge carrier. Let's consider identically charged particles moving in a conductor of cross-sectional area A, as shown in the figure here. The volume of an element of length delta x of the conductor is A delta x. If n represents the number of mobile charge carriers per unit volume, the number of carriers in the volume element is NA delta x, and we get the relationship shown here. If the carriers move with a constant average speed called the drift speed, V sub d, the distance they move in the time interval delta t is given here. Delta x equals Vd delta t. That means we can write delta q as shown. Delta q equals NAV, that's the N is the charge density, AVD delta T times Q. Let's divide both sides by delta T and make the limit. So I is equal to the limit as delta T approaches 0 of delta Q over delta T, which is equal to NQVD V sub D A. Now, although electrons move with average velocity Vd, collisions with atoms cause sharp momentary changes of direction. Let's see if we can understand what drift speed means. Think about a conductor where the charge carriers are free electrons. If the conductor is isolated, these electrons undergo random motion similar to the motion of the molecules in a gas. The drift speed is normally much smaller than the free electron's average speed between collisions with the fixed atoms in the conductor. With the fixed atoms of the conductor. When a potential difference is applied between the ends of the conductor with a battery, for example, an electric field is set up in the conductor, which creates an electric force on the electrons, and current is established. In reality, the electrons don't simply move in straight lines along the conductor. Instead, they undergo repeated collisions with the atoms of the metal, and the result is a complicated zigzag motion with only a small average drift speed along the wire, as illustrated in the figure. The energy transferred from the electrons to the metal atoms during a collision increases the vibrational energy of the atoms and causes a corresponding increase in the temperature of the conductor. Despite the collisions, the electrons move slowly along the conductor in a direction opposite E with the drift velocity Vd, V sub d. The drift speed in a conductor is typically very low. For example, electrons might take an hour or more to travel 1 meter. You might be wondering why a light bulb turns on almost immediately when you flip a switch. You can think of an analogy of water flowing in a pipe. If a drop of water is forced into one end of the pipe that is already filled with water, a drop must be pushed out at the other end of the pipe. Although it may take an individual drop a long time to make it through the pipe, a flow initiated at one end produces a similar flow at the other end very quickly. In a conductor, the charge in the electric field that drives the free electrons travels at a speed close to that of light. That's the change in the electric field. So when you flip a light switch, the message for the electrons to start moving through the wire, which is the electric field, reaches them at the speed on the order of 10 to the 8 meters per second. So the electric field travels at light speed, but not the actual electrons. They move at the drift speed. That ends this section. Next, we'll discuss current and voltage measurements, which is section 17.3.